Hello everyone, hello guys. You are welcome to another series of my lecture on engineering metallurgy, lecture note 3. I am Dr. B. Dan-asabe. I hope you will follow me to enjoy this lecture. This is the outline of this lecture notes. We're going to be looking at heat treatment. We're going to look at the major types, that is heat treatment of steel, annealing and conventional heat treatment. And lastly, if time permits, we shall look at hardenability, which is an aspect of quenching. These are the reference materials used in producing this lecture note. So we start with heat treatment of steel. What is heat treatment? Heat treatment basically is used to improve the mechanical and metallurgical properties. Mechanical properties like strength and hardness and ductility, while metallurgical property and the microstructure, possibly microstructure from a coarse grain structure to a finer grain structure. So one of the primary advantages of steel is their ability to attain very high strength and also retaining some aspect of their ductility, and this is dependent on also the amount of carbon content present. So here we are saying that steel can be strengthened by the amount of carbon content and also by heat treatment. So let's look at by the amount of carbon content. We can see here, as the carbon content is increased, the strength, the yield strength and the ultimate tensile strength also increases, though there is a dropout in ductility. So carbon content increases strength, but negatively affects ductility, which is the elongation here. So also in terms of hardness, because strength and hardness, they go together. As the carbon content also is increased here, as we can see increase in the hardness for all these three curves. So now with respect to heat treatment, heat treatment also improve the mechanical property, basically strength and hardness. So here this heat treatment carried out is called conventional heat treatment, and this is called basically conventional heat treatment is a hardening process, and these two here, they are the annealing processes, the types of annealing. You can see they both improve the hardness value, though conventional heat treatment is more significant, as you can see, in increasing the hardness. So let's start with annealing. What is annealing? Basically, it is a heat treatment process whereby material is raised to a higher temperature and then held for a period of time and then slowly cooled down. So why is annealing carried out? It is carried out to relieve stresses. Here, when material has a component that has undergone machining process, will have leftover stresses. So these leftover stresses, if they are not removed, they can weaken the material and cause failure. So is one of the major reasons why annealing can be carried out. Secondly is to increase softness or ductility and toughness. So ductility is a very important property of an engineering material. A material that is ductile signals when the load is increased, it gives a signal before it fails. So it kind of prevents abrupt failure, because the material can extend more within the plastic limit, within the plastic region before it can fail. So toughness is an aspect of ductility and is an aspect of ductility and strength. So annealing increase ductility and some aspect of strength, and then produce a specific microstructure, that is here change in the microstructure from possibly a coarse grain structure to a much finer grain structure, because a much finer grain structure improves mechanical property. Any annealing process, the process here in annealing consists of three stages which I have said earlier. heating to a higher temperature, to a desired temperature, cooling or holding or soaking at that temperature, and finally cooling. So these are the three stages of annealing, and it also must also be reckoned that a too high change in temperature should be avoided, because that can cause cracking within the material. So let's look at this diagram here. So this is the basically the summary of annealing. Here is the recovery stage, which is the heating stage. Here some physical properties can be recovered, such as thermal and electrical properties. Here is the relief of the stored strain energy from a much higher level to a lower energy state. But in this stage here, mechanical property is not really actually altered. As you can see here, this is the initial stage A before the annealing. This is the heating stage. So basically other properties can be recovered, but basically here the mechanical property is not really altered yet. It's just a change of energy from a higher state to a lower state. As you can see also here, the grain size here is much the same. There's not much change from A and B. And here is the recrystallization stage. Here is where there is a replacement of the worn out or deformed grain size with new ones. This is it here. These grain sizes that are deformed have been replaced by new ones here. So in the second stage here, the holding stage or the soaking stage, you can see here there is increase in ductility, which is one of the primary aspect of annealing. And then you can see a drop in tensile strength. So as ductility increases, there is also a drop out in strength. So these are the new replaced recrystallized grains. And then lastly, the cooling here is the grain growth. So during the cooling, the grain growth should be properly monitored, so that to avoid the growth of abnormal grains. So what is stress relief? We've been talking about removing stresses, relieving stresses. Why? Internal stresses may develop. How does it come about? It comes about as a result of plastic deformation, such as machining operations, such as turning operation, cutting operation, or drilling operations, or grinding operations. So this can cause plastic deformation in the material, and there could be what we call leftover stresses or residual stresses left in the material. Also, secondly, it's why there is need to remove these stresses. This is stress relief. Secondly, is because of non-uniform cooling of a piece or a component that was fabricated at an elevated temperature. An example of this is a welding or casting. You know, when you have a cast, it means before pouring it onto the mold, it was molten at a very high temperature. So during the solidification of the molten metal, if there is non-uniform cooling, this can also cause internal residual stresses within the component. Or welding during cooling, if the cooling is not properly monitored, it can also cause internal residual stresses to be in the material. And lastly, because of phase transformation, here when you have a transformation from a solid solution state to another phase, which is a dual phase, here from a single phase to a dual phase. That's why it's said that from a parent to a product phase. So let's look at an example of this. Here, this is the diagram. For example, here, if we have an alloy at 10% by weight tin, and at around 200 degrees. Here in this is solid solution alpha, single state region. So as it's being cooled, the moment it passes this solvers line, it crosses this solvers line, it will change to alpha plus beta. So beta will begin to form and it will change to, so here during this cooling, if care is not properly monitored, and depending on the two materials, lead and tin, they have differences in their densities. Tin is around 7 plus above, while lead is around 11 plus above, or 11 point something, or tin is about 7 point something. So during the cooling, change in transformation, also internal stresses, can occur, and that can cause the stress. That can cause residual stresses in the final or product, or in this dual stage. And thus these residual stresses needs to be removed, and they are removed by a process of annealing. So let's look at the various types of annealing procedures. The first one here is normalizing. Here is basically to refine the grains to a much finer ones from a coarse one. This is done, the cooling here is done in the open air, and it is done usually on the alloy steels, either low or high alloy steel. And during the cooling, anyway, we are going to look at the diagram, we'll understand it better. And then full annealing here, also at least 55 degrees above the upper critical temperature. Here the difference here is cooling is done in the furnace. It is allowed to furnace cooled. Here usually it is carried out on medium or low carbon steels that have experienced plastic deformation. So after experiencing or being subjected to plastic deformations, the inherent stresses, the residual stresses developed in these steels needed to be removed, and then full annealing is carried out. So let's look at the diagram of normalizing, the region where normalizing can occur. So this is the this V shape here, can see, is the region where normalizing is being carried out. So any of this alloy, any alloy of the carbon or of the steel here, with respect to the carbon content, will have to be heated above the these two lines. We call them the A3. In some textbooks they use A3, but here they're using AC3 and ACM or ACCM. So basically it's referring to this V line here. So anything above it, the alloy has to be heated at least 55 degrees above it, and held or soaked at that temperature, and then allowed to cool. But for the full annealing here, it is like this this line here, like an L here, the AC3, or what we call A3 and A1 line. So either in this diagram here they are adding CCC. So that looks like an L. This is the region where full annealing is done. So anything with this, the heating has to be done above this, at least 55 degrees above it, and allowed to become to change product, because when you're moving from this phase to the another to this, there is a change in structure. So this is basically the difference between normalizing here and full annealing. We're also going to look at the third one, which is ferrodizing. Okay, this is it here, which I've explained. The V here represents normalizing, where the one that looks like an L, like a flattened L, is the full annealing. Actually here, this is an excerpt, an enlarged view of this eutectic region here. And then the last type of annealing process here is ferrodizing. Here it is carried out at least at a temperature below the eutected temperature, and allowed to be soaked for about 15 to 25 hours, or at a temperature just above it, or alternating within the eutectic temperature. So let's look at it here. This is what it means: either below the A1, usually we call this A1, or above the A1, or alternating between this region, and then finally cooling. This is ferrodizing. So usually it's carried out on medium and high carbon steels that have also been subjected to plastic deformation. This is the micrograph or photomicrograph of the spheroidized steel. You can see the background here is the ferrite, while the small spherical circle shaded are the cementite. So this is much more ductile than this, though this one is also, this is just partially spheroidized perlite. Actually it's perlite, but then it has been just partially spheroidized. So you can see the spheroidized circles there within. So this is more ductile than this. Looking at the nature of the cementite, the background here actually is the ferrite. The continuous face is the ferrite, which is the background. Also here the continuous face is the background. So we are done with annealing. Next is the conventional heat treatment. The conventional heat treatment basically is a hardening process, and it involves 3 stages: the austenizing, the quenching, and the tempering. So we are going to look at each after the other, or one after the other. Basically, when we say conventional heat treatment, here the cooling is being expedited by rapid cooling. And rapid cooling, unlike during the annealing process, here it is done with an expedited media, either water, oil, or fast moving air. We remember that during annealing procedure or process, it is allowed to cool under normal atmospheric cooling condition. So let's look at each of them. Austenizing basically is heating to the austenite region. Quenching is the cooling. In this case, it is the rapid cooling. And then tempering. So after quenching, the material becomes extremely very hard and strong, but then it loses most of its ductility. And so to regain this ductility, tempering is being carried out to restore some portion of the ductility. So let's look at them one after the other here. This is the summary here, as you can see. So as I've said earlier, the process starts with austenizing. Austenizing means heating to the austenite region above the A3. A3 is eutectic temperature. Above the A3, sorry, A3 is the yes, A3. Sorry, A3 is not the eutectic temperature, but this is A3 here, at least above it. So heating above it, this is the eutectic line here, and this is the eutectic, right? This horizontal line. So austenizing begins with heating above the A3 line. So just as in annealing, but in this case, instead of cooling under normal atmospheric condition, it will be cooled fast. We call it rapid cooling or quenching. So as we cool down here, as it crosses this S curve is supposed to be specific for each alloy. In this case, this S curve is constructed for steel, or for what we call plain carbon steel. So, but for any material that you want to carry out this process, it must be established. In this case, this is an established S curve for plain carbon steel. So as it's being cooled fast, we have a new structure. Instead of it to cool down and form ferrite and cement, ferrite and perlite, it will not be able to do that, because the cooling has been altered, the normal atmospheric cooling has been altered. This is a rapid cooling, and so because of that alteration, the initial structure that is supposed to be produced will be distorted, and a new structure will result, and this structure is called martensite. So this is as you cool below this, martensite begins to form, and then as you cool below this, martensite is fully formed. So if the cooling is stopped in between, it means martensite, the material will not be fully martensite. So there is also a diagram. So after the cooling, it will be held for some period of time. At this stage, the material is extremely strong and hard, and then in order to restore some portion of the ductility, tempering will have to be carried out. So let's look at this diagram here. This is still the S curve for plain carbon steel. When we say plain carbon steel, we mean the steel is not alloyed, it's unalloyed. So this is it here. So if, for example, we do the fast cooling here, what we are going to have this martensitic structure. But when the cooling is allowed to follow the normal equilibrium cooling under atmospheric condition without aiding the cooling, this is what the structure is going to be. In this case, the cooling curve will pass this. So this is the region where perlite is being formed. So as you pass this, the upper portion of the S, perlite begins to form. It begins to form initially here. So as it crosses the 2S, excuse me please, as the curve crosses the 2S, perlite is fully formed, and then the cool down to the room temperature. As you can see, this is slow cooling and this is fast cooling. So as a result of the fast cooling, instead of perlite to be formed here, there is going to be distortion and alteration, and a new structure, martensite, to be formed. So now if the cooling is done not too fast to form martensite and not too slow to form perlite, what we are going to have is bainite. So this is the region temperature at which bainite can form. So as the cooling initially is fast and then held on to cross the center of the S, so as it crosses the center of the S, bainite begins to form, and then finally as it crosses the other S, bainite is fully formed and it will be cooled down. So this is the structure of bainite. So another scenario here is if it happens that for the martensite, the fast cooling, the final cooling temperature was stopped in between the MS and MF, so it means our product is going to be what? Austenite and then martensite. So we are going to have the final product is going to be austenite, since it's not allowed to fully formed because it was not allowed to cross the other S line. So similarly here, if during the holding it was done at the center here, it was not allowed to cross the other S, so the final product after cooling will result in the austenite. It means some austenite will not be fully transformed to bainite, so it will be a mixture of austenite and bainite. And similarly here, if the cooling was stopped around here, it means what has started forming was perlite, and so the final product will be a mixture of austenite plus perlite. So I've already explained this, that during austenization, the steel is heated to the austenite field gamma and then held for some sufficient amount of time to dissolve into cementite, which is the carbide component, and perlite. Austenization temperature is a function of the carbon content. Here what it means is that you see austenization temperature, as the carbon content is increased, austenization temperature decreases, this line here, because it has to pass this line before it becomes austenite, and also after it becomes to a minimum at 0.76, and then it begins to increase. So this is what it means, that line. This is what it means. Yeah. Then the third point here, the first stage in the formation of the austenite here. So here is explaining how austenite is being formed. So it's from ferrite and cementite as you heat up it will nucleate these two to become, or the carbide here, cemental, will nucleate into the ferrite to become austenite. That's this. And to minimize the time, at least 55 degrees is sufficient, approximately hitting at least 55 degrees above the austenite line. So it must have to cross at least the V line at least 55 degrees above any point of the V line to be fully austenized, or to fully formed austenite. And then the quenching, which I've explained all this in the time temperature transition or transformation diagram. The next is the cooling, which is the quenching. Here, as the cooling is being done, here is explained that if the cooling being done is the normal cooling under atmospheric without aiding the cooling, it means what you are going to have is going to be ferrite and perlite. This is the normal product that is going to be formed, and these two is the same thing as ferrite and cementite, because within here there is another ferrite and cementite. There is another form of the ferrite and cementite. So basically these two products are ferrite and cementite. But if the cooling is being in this case here, we are saying that the carbon atoms are ejected. So from the austenite, the carbon atoms will be fused or ejected to form cementite, and this cementite is a component of the perlite. But now if the cooling is being done very fast, very rapid, so instead of the carbon atom to diffuse, it will not have time to diffuse because of the distortion, and it will form a new structure called martensite. And the crystal structure of this martensite is BCT structure. And martensite is extremely hard and strong, so it's a very high strength structure, high strength and high hardness structure with a BCT crystal structure. But then, as we have explained there, that if the cooling was not done to cross the 2s, you won't have a full product. So on aspect of the martensite being formed, the degree to which martensite is being formed in the alloy or in the component that is being that the process of conventional heat treatment is being carried out is called hardenability. The degree to which martensite is formed, it means whether martensite is formed 80%, 50%, 100%. We relate that with this parameter called hardenability. If it's 100%, we now say it has high hardenability. Though there is a benchmark that anything above 50% within the material, if martensite is formed at least above 50% all through from the surface to the interior, we say that it has high hardenability. So these are some of the quenching media. During quenching media that can be used for the rapid cooling, and this is the most that gives the fast cooling, the brine, and then followed by tap water, followed by salt at a much higher temperature, and followed by oil, and then lastly still air. Still air means normal atmospheric cooling. So you can see that it is the least media in quenching, the one that gives the slowest in terms of cooling the metallic or cooling the alloy component. So lastly, after austenizing, quenching, what we have is an extremely hard and strong material to regain some portion of the ductility, but then the material becomes very brittle. So to regain some portion of ductility, we have to temper. Tempering basically is reheating to an intermediate temperature. This is the temperature tempering is being carried out. At least it should be at least lower than this eutectic temperature, but then the higher the temperature, the more you can regain the ductility, but then some aspect of the strength will also be lost. So this is it, and this is the holding time. You also have to hold during tempering, and then finally you cool. So here, this is it. As this is tempering temperature. As the tempering temperature is increased, you have more ductility. You can see reduction in area increases. But then at this point here at 300, you can see you still have regained some strength though here is as quenched before tempering. So okay, we are not sure here because it's still at a high temperature. Here is not as quenched. Here is at, if it's at without heating, then we say is as quenched. That's after quenching, when the material becomes extremely hard. So at 300 you can see the strength has begun to go down, though we can gain some portion of ductility, but then the higher ductility we gain, the lower the strength. As you can see, as at 500 you can see the amount of ductility we can get, about 50% reduction, but then the strength has fall out to around less than, to around 1200 megapascal. Also, strength and hardness, they go together. As also, this is as quenched, it means without tempering being carried out. So as the temperature drops, though this one is with at Fahrenheit, so you have to be careful. The maximum temperature is about, you can temper, should be less than 727, the eutectoid temperature, not eutectoid temperature. But then remember, as the higher the temperature you quench, you can see the lower also the hardness. We have come to the first part of our lecture. The next lecture is going to be on tempering. I hope you enjoyed my lecture. Thank you very much. Goodbye.